All right, so now let's talk about exponential decay. And you will notice here that the equation is almost identical to our growth. The difference is right here we have a negative in our exponent. So the difference between exponential growth and exponential decay is that you're going to have a negative in the exponent. Okay, so that is the only difference in the two formulas. Let's look at the graphs here. Exponential growth, you'll notice, starts small and gets bigger over time, whereas exponential decay starts large and gets smaller over time. Things like radioactive waste and things like that decay over time. Okay. Decay rate and the half-life are related like this. If I know the half-life, that's what T stands for. If I take the natural log of 2 and divide it by the half-life, it will give me the decay rate. Okay, same is true if I know the decay rate. If I take the natural log of 2 and divide by the decay rate, it will give me the half-life. Okay, this is also going to be true for growth rate and doubling time. They are related in exactly the same way. So you can use either one of those. If you knew the doubling time, you can take natural log of 2, divide by the doubling time and get the growth rate. If you know the growth rate, you can take the natural log of 2, divide by the growth rate and get the doubling time. So same thing for decay rate and half-life and growth rate and doubling time. All right, so let's look at an example. Here we have plutonium-239. It has a decay rate of 0.0028% per year. Now remember, even though this is a decimal, this is the percentage. So we need to change that into its decimal equivalent, which is 0.000028. Okay, so we're going to have the natural log of 2 divided by 0.000028, which gives us 24,755 years. That is your half-life. That is a long time. Okay, so remember, always change your decimals, your percents to their decimal equivalent. Okay, here's a couple more examples. So this time we know the decay rate. Now remember, that's going to be 0.023. Okay, always move your decimal 2 to the left. So we have the natural log of 2 divided by 0.023, which gives us 30.14 years. And in the next example, we have the half-life. So we're going to take natural log of 2, divide it by 13 days, and we get that our half-life is 0.0533 or 5.33%. Okay, so that would be the decay rate. Make sure you are not mixing the percent and the decimal. Okay, this would be the decimal form. You cannot put a percent sign on this. This is the percent equivalent. All right, here is another example. This one's about carbon-14 and carbon dating. So if you ever wondered about carbon dating, this is how they do carbon dating. Carbon-14 is in every living thing. So when something dies, its carbon-14 starts to decay. So we can use that fact to date anything that was at one point alive. So the archaeologists found the linen wrapping from one of the Dead Sea Scrolls had lost 22.3% of its carbon-14, and we want to know how old the linen wrapping was. We also know that carbon-14 has a half-life of 5,730 years. Okay, so we want to start by getting some more information here. Let's see if we can't use this half-life to find our decay rate. So K equals ln2 divided by the number of years. Okay, this is not a decay rate. This is how much carbon-14 we have left. It's not how quickly it's gone away. It is how much of it has been taken away. So that tells us how much is left, not the rate at which it was decaying. Okay, so natural log of 2. So we have 0.000121. So that is our decay rate. Let's go ahead and put that into our formula. So we have P of T equals P sub 0 E negative 0.000121 T. But we're still missing an awful lot of information. So this part takes a little leap of faith. I want you to think about this. If we think about what percent of the carbon-14 is there when something dies, or at the beginning of time, you could say, that would be 100%. So when we started, we had 100% of our carbon-14. Now we know that right now, what we have is 22.3% less than what it started, which would mean that it was 77.7% of what we started with. Now we have enough information that we can solve. So we're going to divide both sides by 100. We get 0.777 equals E negative 0.000121 T. All right, now we want to get this T down to a place where we can work with it. So in order to solve this, we're going to have to apply a natural log to both sides. So the natural log of 0.777. Remember, when I apply a natural log to something with a base of E, the net effect is that it brings this exponent down to a place where we can work with it. Okay, and then we need to divide both sides by our decay rate, which is 0.000121, and that will give us T. So let's go ahead and see what that is. So I have natural log 0.777 divided by so T is 2,085.25 years. Okay, so that is how old these scrolls are, or at least the linen wrapping. Okay, here you'll notice they rounded theirs a little different. They went farther out, which is why theirs is 2,086 and ours was 2,085. All right, the next one. Now, what we're doing here, we've got grandparents, they want to put some money in an account today. They don't know how much to put in today, but they know that they need it to grow to $10,000 by the child's 20th birthday. So they also know they have an account. Interest is compounded continuously, so that gives us the base of E at 4%. Remember, that's going to be 0.04. They want to know what to put in today. So we're going to start out by using this equation. So we have Let's fill in the pieces we know. We know we want it to grow to be 10,000. We don't know what we put in today. We do know that it is 4% interest, and we know it will grow for 20 years. Now, this side is just a number. So we can find out what that number is and divide it off of both sides. In fact, let's just leave it like it is. So we're going to have 10,000 divided by E.04 times 20. And that will give me my initial investment. So let's see what that is. 10,000 divided by so that looks like our initial investment needs to be $4,493.29. Okay, before we continue on, I want to look at this equation a little more. So if we think about the parts of this equation, okay, so we had P of t equals P sub 0 EKT. And in order to solve this, what we did was we divided this off of both sides. So we had P of t over here, and we divided it by e to the kt, and so that was what would give us our initial investment. Okay, we don't like fractions. We've already determined that. So let's see what we can do to make this not a fraction. Now remember, P of t is standing in for our current value. E to the negative kt, we bring that up, equals P sub 0. Okay, so instead of setting this up like a growth problem, present value problems are actually decay problems. Okay, so we enter in the amount we want it to grow to, e to the negative kt, and it will tell us what this amount is. So we don't have to switch the equation around. So you want to remind yourself that present value problems are decay problems. So you're going to use that decay function for all your present value problems. All right, this is the end of chapter 2. So we will be starting chapter 3 next time.